Hi everyone, this is Spectre P and we are Spectre AI. In this video, we will see that measurement device independent QKD is often presented as the solution to detector attacks in quantum key distribution, but what it actually does is narrow the threat model rather than eliminate it. MDI QKD removes trust in the detectors by outsourcing measurement to an untrusted relay, which does mitigate specific detector blinding attacks, but the system still relies on classical coordination, timing alignment, protocol execution, and statistical inference to reconstruct security. Those elements sit outside the quantum proof and remain vulnerable to bias, manipulation, calibration drift, and software-level interpretation errors. In practice, the attack surface doesn't disappear. It shifts. The protocol becomes secure under a different set of assumptions, not fewer assumptions. That means MDI QKD improves resilience against one class of failures, but it does not resolve the core issue of inferring security from real hardware behavior. This is why deployed quantum systems continue to fail in ways that proofs do not anticipate. The mathematics constrains an idealized model, while the system operates in an environment where trust is reintroduced through implementation. MDI QKD is often described as fixing detector attacks, but what it actually does is much narrower. It removes trust in Bob's detectors by pushing measurement into an untrusted relay, which blocks a specific class of detector-side exploits. But everything else, clock synchronization, basis sifting, error correction, and parameter estimation, still lives outside the quantum proof. Security isn't directly observed here. It's inferred from expected statistics, and when real hardware deviates from those expectations, the protocol has no way to tell you why. MDI QKD removes one trust assumption, but it doesn't eliminate hardware behavior, calibration bias, or classical leakage. It just moves where the assumptions live. Here's where MDI QKD actually falls short. What it really removes is detector-side trust. By pushing the measurement into an untrusted relay, Bob no longer has to assume his detector is honest. But that doesn't eliminate risk, it just moves it. The attack surface shifts into timing windows, bias and drift in real hardware, and classical control logic that sits outside the quantum model. Those effects are invisible to the security proof. The protocol can look valid, pass all expected checks, and still be compromised, because the security is inferred statistically, not directly observed in the physical system. This plot shows the core security gap in real quantum systems. The proof assumes stationary parameters, so security bounds are computed from long-term averages, shown by the flat expected line. But real hardware never behaves that way. Instead, it drifts slowly over time and occasionally exhibits transient deviations that are short-lived but exploitable, and because those deviations are averaged out during parameter estimation, the protocol still appears secure even while the instantaneous behavior violates the assumptions of the proof, meaning the attack doesn't break the math. It breaks the physics the math assumes, which is why the system looks valid, passes checks, and still leaks key material during these transient windows. This diagram shows where the real security gap actually forms, not in the protocol or the proof, but in the layers in between. At the top, the protocol and proof layer assumes clean, well-modeled behavior. Below that, the measurement and estimation layer is where parameters are inferred from real signals, averages are computed, and bounds are derived. But the hardware runtime layer underneath is noisy, drifting, and time-varying. Calibration bias, slow drift, and transient behavior flow upward into the estimation layer, while unmodeled dynamics leak upward into the proof assumptions. An attacker doesn't need to break the protocol. They exploit short-lived deviations during these transitions, where the math still looks valid but the system has already moved. That's why the proof holds, the numbers pass, and the key is still compromised. Security proofs don't fail because the mathematics is wrong. They fail because they assume an ideal world. They assume perfect single-photon sources, perfect detectors, trusted device behavior, no side channels, and flawless calibration. Those assumptions are necessary to make the proofs work, but none of them hold in deployed systems. Real quantum hardware drifts, leaks information, behaves non-ideally, and exposes subtle physical degrees of freedom that never appear in the equations. As a result, real systems violate every one of these assumptions. And attackers don't break the math, they exploit the gap. When quantum systems leak information, it doesn't look like hacking. Nothing crashes, nothing alarms, and no software bug is exploited. Instead, information leaks through physics, through tiny timing differences between detectors, intensity-dependent detector behavior, and unintended optical emissions like back reflections. These effects are subtle, but they're measurable, and they create side channels that never appear in security proofs. And the most dangerous part is this: the system still passes every protocol check. QBER stays below threshold. Keys are generated and operators believe the system is secure. In real quantum systems, detectors do not respond uniformly in time. Each detector has a finite detection window, and those windows are never perfectly aligned. Detection efficiency varies within the window itself, meaning the probability of a click depends on exactly when a photon arrives. By deliberately shifting the photon arrival time by a small amount, an attacker can bias which detector is more likely to register the event, effectively steering bit outcomes. Crucially, this manipulation does not introduce obvious errors. The protocol continues to operate normally, keys are generated, and QBER remains below threshold, even though information has already leaked. What all of these examples point to is a simple but uncomfortable truth. Security is not a proof property. Mathematical proofs secure protocols in isolation, but protocols do not run in isolation. They run on hardware, in physical environments, with imperfect components and unavoidable side effects. Security emerges from the interaction of all these layers: protocol, hardware, and environment. And if any one of them leaks information, the entire system leaks. That's why real-world quantum security cannot be evaluated on proofs alone. It has to be evaluated as a system. So here are the key takeaways. Security proofs assume ideal devices, but real systems never meet those assumptions. Most real-world quantum attacks don't break mathematics. They exploit physics, allowing information to leak quietly without triggering obvious errors. That's why security can't be evaluated in isolation. It has to be evaluated as a system, where protocol, hardware, and environment all interact. And that's the core lesson here. Provably secure does not mean attack secure. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.